So I'm Trammell Hudson with Lower Layer Labs, and I want to talk about the big question in building secure systems is how do we prevent unauthorized code from running on it? And it turns out it's pretty simple. We can turn on verified boot, like boot guard on Intel CPUs. And verified boot takes over when the CPU comes out of reset. It does a signature check on the firmware, and if the signature check doesn't pass, it just halts the CPU. And if it does pass, then it runs the firmware, and the firmware can then validate the signature on the OS can validate signatures on the applications, and then no unauthorized code can ever run. All right, thanks for coming to my talk. I hope you all have a wonderful day 2 here at hardwear.io. Let's go back to that slide. In security, things don't tend to be that simple. That building a system that halts on the first sign of failure may be very attractive if you're building a closed source system that is a walled garden that is never going to run any sort of user code. But this comes at great expense to the user freedom to control what runs on their computer. It also is really has very brittle failure modes. It's not resilient to hardware failures or to recovery from attacks. And it also has no way to prove to the outside world that it hasn't been compromised. So we need some way for systems to be able to attest what is actually running on them. The freedom is one that's really important to me. As was mentioned in the introduction, 10 years ago I started a project to build open source firmware for Canon cameras. The Magic Lantern project has let hundreds of thousands of camera owners write extensions for their cameras that let them use them the way they want, provide the features that they want. I've also been thinking a lot about how to build more secure commodity systems and started the Heads firmware project a few years ago that's looking at how do we build slightly more secure laptops with what's available in off-the-shelf parts. I'm also a core contributor on the Linux Boot project, which is looking at providing similar sort of security guarantees with free software for servers in the firmware. And for me, freedom has 2 main components. We need the signing keys for the firmware, and we need documentation. The signing keys are absolutely vital because a lot of open source projects, a lot of embedded projects are built with open source software, but because we don't control the root of trust, they're at risk of what's called TiVoization, where it's open inside, but we can't change it. So it might as well be a closed source product. The firmware is also a really privileged position where things running in firmware can bypass pretty much any security guarantees that the OS or the hypervisor might want to use. And it would be really bad if OEMs abused that position to install malware or adware that users didn't want. Even if they're not acting maliciously, as Jess Frizzell points out, a lot of these vendors aren't in a position to be able to debug their own firmware because on most of these systems, they didn't write it. Most of the UEFI firmware comes in the reference implementations from Intel, AMD, and packaged up by the Tiano Core EDK2 kit. Independent BIOS vendors do occasional pulls from that Git tree and then are paid by device manufacturers to port it to different main boards. And these device manufacturers are manufacturing it for OEMs who typically only write a very small percentage of the actual software that makes up the firmware on the system. There's one big exception here, which is Apple, that runs their own firmware teams and is able to do much tighter release cycles because of that. So when a vulnerability or a bug is found, it's probably going to be in the reference implementation, which means that to get it fixed, the IBVs have to pull that patch. They have to get paid by the ODMs to integrate it, or to backport it to older main boards. And they'll really only do that if the OEMs are paying them for a support contract, which means that for many boards, they never ever see any firmware updates. This is bad for usability bugs, but it's especially bad for security bugs, because this means that essentially a lot of this firmware is full of what are called forever day bugs that are going to be there as long as the system is deployed. And we think Linux boot and open firmware has a much better security story because the computer owners can apply security patches and apply them on their own schedule. And they can then share those with the wider community. The problem is we can only do this sort of self-help if we have documentation about what is on these main boards. That without documentation and schematics, we're faced with a pile of parts and connectors and headers. And what happens if you plug into this debug hooks port? What does this sec update jumper do? Why is there a weird daughter card kind of glommed onto this board? Is it supposed to be there? Is it some last-minute revision by the manufacturer? Or is it some sort of hardware implant from the intelligence agencies that are doing a supply chain attack against us? It's probably not a God surge from the NSA, but how do we know? These are some of the problems that Sophia d'Antoine found when her firm was hired to tear down a bunch of Supermicro boards in the wake of the Bloomberg story. That they found inconsistencies between what was on the silk screen and what parts were installed. They found signs of various revisions where things didn't necessarily get updated on the silk screens. And as a result, it was very unclear what parts were supposed to be there, what maybe was added. You can check out her blog post for some more details. There are also lots of just random test points on the boards that we can find out what some of them do through reverse engineering, and sometimes it's really sort of shocking what you can do via these test points. For instance, on this server board, there's what is very clearly a serial console, and if you hook up to it, it prints a prompt that says press enter, and you press enter, and it drops you into an unauthenticated root shell on the BMC. Why is this there? And once you're on that BMC, you have pretty much run of the system. It's connected to the power supply. It's connected to the network so that folks can turn the power supply on and off. It's connected to the serial console so folks can do BIOS interaction. It can provide a USB file system to boot new OSs. It can see what's on the VGA screen to provide a KVM functions. It has DMA access through the PCIe to all of host memory. It can talk to the SPI bus, which means it can install new firmware for the x86. And on many of them, it's also on the LPC bus, so it can steal secrets out of the TPM. This is basically a skeleton key to the system that has an unauthenticated root shell available for a hardware implant to take advantage of. For more details on exactly how you could take advantage of that, you can check out my talk from CCC last year about how mod chips could be installed in the supply chain to bypass, to take over the BMC. Luckily, there are some manufacturers who are publishing their schematics. The Open Compute project is requiring that that boards that they certify come with full schematics. And the hyperscalers are buying these by the hundreds of thousands or millions of boards. And it's really neat to see what goes into building a modern computer. And when you go through these schematics, you can actually see, oh, that's where the BMC debug port is. We should think about what's actually running on there. You can see things like the BMC's JTAG interface. So you can actually make reasoned decisions about should this be connected. This also allows security-conscious sites to review the boards that they receive and validate that they match the designs. Now, not everyone is going to have time to do that. And as Stephanie Land points out, your threat model is not my threat model. But the benefit is that the high security sites that are doing this review, both of the firmware and the hardware, can publish without NDAs. They can talk about what they find, and that improves the security for the entire ecosystem. And that's one of the real benefits of having this user freedom in the firmware. So just like we don't all have the same threat model, we also don't all have the same resiliency and recovery requirements. So if we go back and look at that verified boot case, where the CPU just halts if it doesn't like the firmware, in practice, what does that look like? Well, this is a ThinkPad with a boot guard failure. And other than needing to clean the screen, it's completely inert. There is literally no sign of life. It is indistinguishable from either a bad CPU or a bad battery or some other sort of hardware failure. So there's no sign, was this a failed attack? Is this a hardware failure? And recovering from this requires the ultra-high touch sort of method of popping the bottom and hooking the flash programmer up to the chip to reflash with a known good firmware. Very few sites have the skills and the wherewithal to recover from this sort of failure. And as a result, this was really only going to be done if there's a super high value forensic need or other data on the system. Most folks want some sort of physical presence for their recovery, so sort of a high-touch environment where perhaps you want to set a BIOS jumper, or maybe you want to log into the serial console, or perhaps hold down a key on boot. With free software, these sort of configuration choices, or these sorts of choices become configuration through shell scripts or other simple means. This is no longer a decision that the OEM has to make for you. It's one that you as can make for your own computers. Some sites do want to be able to do network recovery. Samantha Downs from Facebook gave a talk about how they have redesigned parts of OpenBMC on their servers to use a root of trust for recovery, where they now have a certificate authority in their a certificate authority key in their BMC that can validate the users trying to log in to do recovery. And this means they don't have to worry about passwords, they don't have to worry about expiration. And this is no longer something that they had to go to an OEM to ask for. They were able to implement with a few lines of code. A lot of sites are also zero touch. Perhaps you have millions of machines over hundreds of acres in the Utah desert where nobody wants to go maintain them. Or perhaps you put machines in a container that are at a power, out on a power station. Or perhaps you've sunk a bunch of machines in the ocean and can't get a tech out there. These are sort of cases where you do not want a system to hard brick in the event of any sort of failure. And this is where, again, we think open firmware has a really good resiliency story, because we can provide tools, not policy. We can let individual sites choose what works best for them. As David and Andrea pointed out, this lets you solve your firmware problems with the same Linux tools that you would be using to do any of your other sort of system management. And that's a real value for a lot of sites to be able to script these things and recover from failures with the same skill set that they already have. Mostly we've been talking about failures, but recovering from attacks is really hard, and especially attacks that are targeting firmware, because firmware can survive OS reinstalls. Some malware attacks can even install themselves deep into the chipset and require very invasive desoldering to remove. So a lot of places are using the BMC as the sort of out-of-band firmware update mechanism, but this means that now the BMC is inside the trusted computing base. And as I alluded to, I have concerns about that, and so do a lot of other folks. The director of Azure Security points out that the BMCs are really insecure, that they have almost no protections. They have very little ability to recover, and they don't have any way to detect when failures have occurred because they don't participate in the remote attestation. Which brings us to the third sort of part of what I think we need to build more secure systems, which is remote attestation. And in the open community, attestation has been a bad word for literally decades. That in 1999, the free software community rebelled when Intel wanted to add a unique serial number that would allow devices to be tracked. It seems very quaint now that that people were concerned about being tracked on the internet, but it led to very heated flame wars on the Linux mailing lists. But what really turned the community against the trusted computing was a few years later when Microsoft Palladium was announced. And this is back when you could build websites with tables, very Web 1.0. The big concern was that Microsoft was going to add hardware to the computers that would validate the OS and validate the applications. And as was discussed on the mailing list, the whole point of open source is for users to be able to modify the code. And if every modification requires a new signature from Microsoft, that suddenly becomes the end of open source software. So as a result, the Linux community has really not supported TPMs at all. And these trusted platform modules are required by Windows for certain certification, but only Windows uses them. Largely, only Windows uses them for BitLocker and DRM applications. So basically, a lot of the things that people were concerned about. However, they can be used for good. And the Chromebook project is using a lot of the really innovative features on the TPM. That they have things like these monotonic counters that only increment. And these can be used to prevent rollback attacks where folks want to install an older, insecure version of the software. They have the ability to seal secrets in a way that the TPM will only decrypt them if the firmware is unchanged. And a really key distinction here is the TPM will only decrypt them if it's unchanged from when it was sealed, not if it matches some vendor signature. So on a Chromebook, you can install your own firmware and reseal the disk encryption keys and run it with your own firmware without having to talk to Google or get in any approval. The TPM is also used by the Chromebook for doing remote attestation so that Google can decide whether they will trust logins from that from that device. And you can tell Google, I'm using a hacked Chromebook of my own. I want to trust it and log in. And this is, again, not being used to lock out unauthorized devices, but it's to enhance the security for the users. So the key message, TPMs can be used for good. And I hope the open source community comes around to that. There are some folks who are advocating for it. Matthew Garrett has been tirelessly pushing for TPM and trusted computing patches. And he came up with a really innovative way that the TPMs can be used to help secure the early boot process. Where the computer pops up the prompt for your disk encryption password. Because he points out, can you trust the firmware that launched the bootloader, that loaded the kernel, that's running the software, that is now asking for your disk encryption password? And what he proposed is the computer can attest to the user that it's unmodified. And he did this with a sealed secret in the TPM that's shared with a TOTP authenticator. So when the computer boots, if the firmware is unchanged, the TPM will unseal that secret, combine that secret with the current time, and produce a 6-digit code that the user can then compare to what's being displayed on their phone and decide whether or not they trust that the system is unmodified. This is a really clever way to sort of use attestation for the benefit of the user rather than to lock down the machine. it's possible to use this attestation, again, from the server to the user in the same flipped mode. The Molvad VPN provider is published a really nice white paper about how they are going to use attestation to help you decide whether or not you can trust them. So they're going to publish all of their software stack in a reproducibly built manner that you can read through all the code. You can decide whether or not you trust their login and their interactive access, and then generate a hash that you can then compare against the cryptographic signature from the TPM on their servers to decide if it is unchanged from what you've reviewed and audited. The other thing Molvat has done to support this is they have paid 9Elements cybersecurity to port core boot to the servers that they're using, as well as then the micro BMC or open BMC, which means that thanks to their support, the community can now buy a commodity off-the-shelf server and run open source firmware all the way from the BMC power on through the CPU power on, and then all the way into the OS and the software stack, which means they can have an unbroken chain of trust consisting almost entirely of free software that their users can audit and can read and can reason about. And because they've released this into the main line of the core boot tree, everyone else who wants to build servers built on free software can do that. I'm also really excited about some of the developments in enclaves and trusted execution. Intel SGX is a way to run a ring-3 user space process in encrypted memory where the OS or the hypervisor can't see what's happening in that process. And the CPU can sign a cryptographic quote, or cryptographic hash of the application to prove to the outside world that it is running in this secure mode. Signal is talking about using this for doing contact discovery, because they're not like LinkedIn. They don't want to know who your contacts are, but they need to know who your contacts are so they can tell you who else is on Signal. And what they've proposed doing is publishing the code that does that contact matching so that users can review it, verify that they're not storing the data, and then by running that in SGX Enclave, they can provide an attestation that it is running the code that has been reviewed so that you can feel fairly confident that they're not going to leak your contacts and spam them with emails. I'm also really excited about AMD's SEV, which is applying similar encryption ideas to entire virtual machines. So in this case, when you want to launch a virtual machine on a cloud provider, right now they can see everything that's running in your VM. They can see all your secrets. They can read your data. It would be really nice if you didn't have to trust them, if they could be outside your trusted computing base and you didn't have to depend on their administrators. And I think this is a really important step that's going to change the way a lot of us use the cloud. Just like a few years ago, memory management units were a new thing, and suddenly we got protection between processes. I think encrypted virtual machines are going to be the new normal within a few years. Now, just like both SGX and SEV have had some initial problems, the team at the Technical University of Berlin found some hardware attacks against SEV. SGX has also had some side channel attacks. However, they concluded that the authentication protocol and the attestation protocol seemed reasonable. And again, I'm really encouraged and hope that that's going to become the new normal, the table stakes for running a cloud provider. The cloud providers are also doing a lot of innovation on hardware root of trust so that they can have more faith in their own systems. The Google Titan chip is doing firmware validation against their own signatures They also are shipping it in the Chromebooks, and it's able to take over the TPM functions. Microsoft Cerberus is being used in Azure. It also has similar TPM-like functions. They are going a step further in publishing open source and open silicon for it. And so if you wanted to build your own firmware and fuse your own keys, you can do that. It's very interesting that Microsoft from 2002 to 2019 has completely changed their view on a lot of this open source. Amazon also has hardware root of trust on their machines. They haven't provided any details about what's going on inside, so it's not really particularly interesting from the free software side of it, other than that it's important enough for them to be concerned about it. And then Apple has also produced a really neat chip for their MacBooks that does firmware validation prior to CPU reset. And they deserve a lot of credit for building secure by default systems, but unfortunately it is completely locked down so that only Apple firmware will run. It is pretty neat, though, how that one is interposed in the SPI bus. There's a really nice white paper that is worth checking out. All of these are looking at how to protect the x86 from, and in some cases, the BMC firmware. But as Johanna Rotowska pointed out, there's a lot of mutable state and a lot of firmware in our servers. If we look at a modern computer or a modern server, we have firmware in the CPU, we have firmware in the BMC, the NIC has firmware, the GPU has firmware, the disk controllers have firmware, the disks have firmware, the front panels have firmware, some of the fans have firmware, the power supplies have firmware, and I've been able to get code execution on at least one BMC over the PM bus from a power supply, which, it should not be possible, but the big problem is that we're not treating our computers as the distributed networks that they are. We really need to start treating them more as sort of a distrusting distributed network, because they're not one computer. As Whitecork says, it's a whole bunch of embedded devices hiding in a trench coat. So, more seriously, NIST has published some guidelines, and these were mentioned yesterday in the supply chain discussion about how to try to think about this network of devices inside our computers. And the guidelines are a good start, that they identify the 3 roots of trust for update, for measurement, and for recovery. And they talk about how to try to extend this sort of in the tree of devices. Unfortunately, a lot of them depend on the fact that perhaps the device manufacturers are trustworthy. And we're facing a lot of trouble on our supply chains, where chips that look legit internally may be completely counterfeit. And in the case of these FTDI chips, it's a completely different CPU running software that's emulating the original one. This was done by a contract manufacturer to save on cost, but you can imagine the security implications of having a completely different CPU inside some of these things. We're also, most of the resiliency guidelines don't really address the possibility of hardware interposers, like the TPM Genie, that can intercept all of the TPM traffic and circumvent the root of trust that the TPM provides. Or attacks like the spy flash TalkTal that Peter Bosch and I came up with, and were able to defeat BootGuard. We turned that into an open source tool called SpySpy that is really useful for investigating early boot time security. And I gave a talk about that last week at CCC Camp. So hopefully, in this brief talk, I've been able to convince you that verified boot is not the way to go. That if you're building systems, that you should think about how to embrace user freedom to make more resilient systems, and how to also be able to attest that what's actually running. And if this sort of thing is of interest to you, we have a Slack group where a bunch of us hang out and would love to hear your thoughts on how to build more secure systems. And hope you all have a wonderful second day here at hardwear.io, and I'd love to take any questions you might have.
Hello. So, I'm just curious, how do you think such an open source boot could handle Intel microcode upgrades properly?
So,
when you have a commercial processor with a closed source microcode upgrade, and it will cause changes in the operation of this full system at the next boot.
So the question is about what about closed source blobs like microcode updates and other things that are required to boot modern Intel CPUs. And I did sort of gloss over that in for instance the Mulvad core boot port. It is using Intel FSP and it is applying microcode updates. So there's some things like the SGX takes into account the microcode revision as part of its security version number. So the quote that you receive, the cryptographic quote from the SGX, tells you if the microcode has changed. Because microcode can circumvent a huge number of, you could potentially introduce a lot of security vulnerabilities. In terms of being able to just integrate microcode updates, that's not a problem. Linux can load microcode. The CPU also will look at what's called, or the x86 will look at the firmware interface table and see if there are any microcode updates for it prior to starting the bootguard ACM or any of the other firmware. It actually does that before executing any user mode CPU instructions. The concern about could they circumvent security through doing so? They could. However, attestation potentially gives us a way to detect that. Because if the part of the firmware that includes that microcode update is hashed into the TPM or the other root of trust, the attestation would tell us whether or not an adversary had installed a new, or a different microcode. So it is a concern. I think it's somewhat ameliorated both by the things like the SGX enclave quote as well as the measured boot approach of using the TPM.
Okay, thank you for your presentation. And regarding SB 800-193, I believe this was published a year ago or a couple of years ago by NIST. And still, this is not fully recognized by the industry or by people, by society. But I think this is one of the most clear document to describe the firmware resiliency guideline as a firmware resiliency guidelines in front of the public. And then, so I wonder how this can be accepted in the near future. And so what do you think about the potential acceptance of this document in the as a kind of the de facto standard, maybe?
So I completely agree that the 800-183 guidelines for platform resiliency guidelines are really well written. They're really quite clear as far as standards go. I'm a little bit despairing at the slow pace of firmware updates and things like the Vincent Zimmer, who's the lead at the UEFI group at Intel, published a white paper in I think 2014 about turning on the IO MMU in the firmware to prevent DMA attacks in the early boot. Other than Apple, I have yet to see a vendor actually enable that. 5 years later. So my feeling is that there are certain vendors who are very motivated to implement things like the platform resiliency guidelines. And I think a lot of it's going to come from the hyperscalers who are buying machines by the hundreds of thousands or millions and can take the time to customize the firmware to their resiliency needs. So I think we will end up with a set of sort of resiliency that matches what the hyperscalers need, and hopefully that will satisfy everyone else's needs. But yeah, in general, but like that slide showed, the firmware world is very slow to fix problems.
Thank you, Trammell.
All right, thank you all. I hope you all have a great second day.